SwayamPrabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. Today I am going to talk about electrochemical grinding and electrochemical deburring. Both are very important processes as long as fabrication of micro features is concerned. You can see the micro products that have been made by micromachining over here. I acknowledge the help of the following: Divyansh Patel, who has written a chapter on electrochemical grinding; Dr. Kuppu Swami, who had written long back a paper in Tribology International, book on advanced machining processes. Organization of the talk for ECG part is following. I will be discussing this separately, ECG as first part and electrochemical deburring in the second part. Introduction, where I am going to discuss about conventional grinding as well as electrochemical grinding, how they compare with each other. Electrochemical grinding machine tool elements and machine tools. Theory of electrochemical grinding. Electrochemical grinding process performance. Applications, some applications. Here I am not going to go into very details, but some applications I will show you about the electrochemical grinding, and then conclusion about the ECG part. Introduction. Conventional grinding characteristics that we know, but it is good to refresh them. Workpiece material can be either electrically conductive or electrically non-conductive, because there is no constraint as long as conductivity of the workpiece is concerned in conventional grinding process. Then conventional grinding gives good surface finish and low tolerance values. It produces bursts, heat affected zone, and thermal residual stresses in the finished parts. In case of conventional grinding, 100% material removal takes place by abrasive action only. In electrochemical grinding, as you can see over here, this is the conventional grinding part where grinding wheel is rotating. This is the workpiece, and there is a contact arc, that is the contact arc between the workpiece and the grinding wheel. In case of electrochemical grinding, as you can see over here, electrolyte is being supplied over here, and you can see the electrochemical grinding, the gap at the exit is more, and at the center, almost at the center or near to the center, is less. So it is continuously decreasing, and the grinding wheel is rotating, and this is the contact arc over here, and this is the contact point, and this is known as electrochemical grinding. Here electrolyte is being used. Here both grinding as well as electrochemical machining are taking place. I will show you. Common electrolytes used during electrochemical grinding are NaCl, NaNO3, and others also can be used depending upon the workpiece material properties. In ECG, workpiece should be electrically conductive. This is the basic condition required, because workpiece is forming as the anode and grinding wheel is forming as the cathode. Electrolyte is used during ECG, that is what I have mentioned to you over here, and After proper filtration, it should be recirculated because electrolyte is quite expensive, and proper filtration and treatment, normally it is being recirculated. For ECG beam, bonding material should be electrically conductive because it is going to be the part of electrical circuit. So, the bonding material of ECG grinding wheel has to be electrically conductive. Grinding wheel acts as cathode and workpiece acts as anode, as I mentioned you a bit earlier. Material removal takes place by electrolytic dissolution, as you can see over here, and mechanical abrasion, that is taking place over here. Mechanical abrasive action is around 10%, or because of mechanical abrasive action the material removed is around 10%, and remaining 90% of material is removed by electrochemical dissolution, that is based on electrochemical machining principle. Higher wheel life compared to conventional grinding wheel, because for only around 10-15% of the material is removed by the abrasive action and rest is removed by the electrochemical reaction or dissolution. Hence, wheel life is higher than what is the wheel life in case of conventional grinding. ECG machine tool, electrochemical grinding machine tool. Simple elements I have shown over here. You can see DC power supply, voltage for regulating, monitoring it, ammeter. This is the insulation on, this is the grinding wheel which is having metallic bonding material and abrasive particles over here, and nozzle spraying electrolyte is shown over here with this particular arrow, and this is the from here electrolyte is taken out to the reservoir, filtration takes place, clarification takes place, then pumping is done, then flow meter is there to monitor the flow rate of the electrolyte. And here is the workpiece, as you can see plus sign is there, so it is acting as anode, and this is the grinding wheel, minus sign is there, that means it is acting as the cathode. Here very important figure, mechanism of material removal in electrochemical grinding can be understood with the help of this. It is rotating in this direction. Three phases are shown, phase 1, phase 2, phase 3. Now you can see here phase 1, phase 2 and phase 3. Now here you can see three phases, and mechanism of material removal in all these three phases are different. This is known as material removed by phase 1. So, this amount of material, or in this zone the material is removed by phase 1, in this zone material is removed by phase 2, and in this zone material removed is by phase 3 or in phase 3. And I will show you the larger size of this figure which will make the things more clear. Theory of ECG, electrochemical reactions, types of electrolytes used in ECM, they can be acidic, basic or alkaline or neutral. Reactions during ECM with iron Fe as anode and sodium chloride NaCl aqueous solution as electrolyte. 2H2O plus 2 electrons, 2E minus, and you get the hydrogen gas H2 plus hydroxide 2H, 2OH. Then you have the iron, minus electrons are taken out from it, so it becomes positively charged, 2 iron ions. Then Fe plus twice OH from here, both of them react and you get ferrous hydroxide FeOH twice. In certain cases you can get ferric hydroxides also, twice Fe plus 4 H2O, that gives you ferrous hydroxides. FeOH twice and FeOH thrice, they are insoluble in water. Positive ions convert as hydroxides, ferrous or ferric hydroxide in case of iron as anode or workpiece material, and here inter-electrode gap is normally less than 1 millimeter, which I showed you in the earlier figure, and it is continuously varying along the material removal zone, and voltage is taken 8 to 20 volts, which depends upon your workpiece requirement, that is tolerances that you require, surface finish you require, material removal rate that you require. No electrolyte is being consumed in the process. As you can see here in this process, electrolyte, that is NaCl or NaOH or NaNO3, they are not being consumed. So after filtration and cleaning, the electrolyte is recirculated. Now 3 zones, this is important to understand now. These 3 zones I have shown here. In zone 1, as you can see, this is in this area that is shown over here. There is no contact of the abrasive particles with the workpiece surface, and whatever material is being removed, it is removed due to the electrochemical dissolution. This is zone 2, that is zone 2 here, and in large view is here. Abrasive particles are in contact with the workpiece, and between the abrasive particles, electrochemical cell is formed and material is being removed due to electrochemical dissolution also. And in zone 3, as you can see here, the grinding wheel and workpiece, the gap is continuously increasing, and material removal is due to electrochemical dissolution only. Tiny electrolytic cell is formed. Now you can see the schematic diagram of the setup. Electrolyte supply is there, grinding wheel is there, electrode conductive wheel is there, and this is the workpiece over here, and this is in contact with the abrasive particles. This is the work table, this is the tank where electrolyte is kept, and this is taken out from here, pumped, filtered and recirculated. And here DC power supply is there. You have the contact with the grinding wheel through this particular shaft, and this is the insulating sleeve brushing. In zone 1, where pure electrochemical dissolution is taking place, wheel rotation helps in drawing electrolyte in the machining zone. As you can see here, this wheel is rotating in this direction, and this is the electrolyte. So it is drawing the electrolyte in the machining zone. Contamination in zone 1 takes place by reaction products and gases. They are formed in zone 1. Electrolytes, electrical conductivity K changes. Electrolyte gets trapped between abrasive grids and workpiece top surface. As you can see over here, electrolyte gets trapped between abrasive particles and workpiece surface. It forms electrolytic cell as shown in the figure. A small amount of material is removed in this zone. Converging inter-electrode gap varies from high to low. As you can see here, inter-electrode gap is large, here it is low. In zone 2, high pressure exists between wheel and workpiece. It suppresses formation of gas bubbles, and you get higher K, hence you get higher material removal rate. I think let me show you once again. This zone 2, you can see here, this is the zone 2, abrasive particles, this is the electrolyte, and here electrochemical dissolution is taking place. In this zone, abrasive grains also abrade the workpiece surface. As a result, they remove material from workpiece and oxide layer is formed. If any on the workpiece surface, material is removed in the form of microchips, or even it can be nanochips, depending upon the depth of indentation of abrasive particle into the workpiece surface. Oxide layer removal helps in electrochemical dissolution because abrasion is taking place. It also removes the oxide layer formed in zone 1 as well as zone 2. Material removal also takes place due to EC dissolution in the electrolytic cell. I have told you here also that these are the abrasive particles, this is the electrolytic cell, and material removal is taking place due to EC electrochemical dissolution as well. In zone 3, there is no contact of the abrasive particles with the workpiece surface, and this is diverging inter-electrode gap, and whole material is removed by electrochemical dissolution only. In this zone, there is no contact between abrasive grain and workpiece surface. Wheel starts lifting off the work surface, hence material removal takes place by electrochemical dissolution only, as you can see over here. Electrochemical dissolution removes scratches and burrs formed in zone 2. As you can see here, in zone 2, material is removed by abrasive particles also, which will form the scratches as well as they may form the burrs also. So, these scratches and burrs are smoothened, removed in zone 3 due to electrochemical dissolution. Process performance of electrochemical grinding process. ECG process characteristics. Material removal rate and surface finish are governed by current density, because you must have studied in electrochemical machining that material removal is directly proportional to the current value. Very high voltage across the electrodes would lead to sparking. This is very important and one should be very careful, because gap is very small and voltage is very high, then sparking may take place and it may damage both grinding wheel as well as workpiece, which deteriorates surface finish and damages grinding wheel as well as workpiece. Now, in electrochemical grinding, it should be G, not C. Material removal rate can be as high as 10 times of conventional grinding, because as I told you in the second slide, that conventional grinding gives you the low material removal rate, but in ECG, material removal rate can be as high as 10 times of conventional grinding on hard materials which have hardness even more than 65 HRC. Feed rate has its own effect on material removal rate and other responses. If feed rate is higher than the required one, then abrasives detach prematurely from the wheel, grinding wheel or electrochemical grinding wheel, which lead to excessive grinding wheel wear. Low wheel life becomes low because abrasives are pulled off from the grinding wheel and cost will be definitely higher. If feed rate is lower than the required one, then it will lead to large overcut, because material removal due to dissolution will continuously keep taking place even though the feed rate is low, poor tolerances and poor surface finish. So, what I can suggest, I can advise is that before using any machining process or manufacturing process, optimization for the workpiece and taking into consideration the parameter should be done to make it economical and give better performance product. Wheel's peripheral or surface speed is normally 20 to 30 meter per second. Process performance, the best tolerances obtained by this process are plus minus 25 micron or even more. Outside corner radius that can be achieved by this process is around 250 micrometer, that is 0.25 millimeter. Inside corner radius you can achieve around 250 micrometer. Surface roughness that can be obtained is usually 0.1 to 0.8 micrometer, which depends upon the conditions you have chosen and the properties of the workpiece material. Surface obtained after electrochemical grinding is free of burrs and scratches. I have already told you that in the third stage, where electrochemical dissolution is taking place only, whatever burrs are formed or scratches are formed in second zone, those are removed in the third zone, because burrs and scratches get dissolved in zone 3 by electrochemical dissolution. You have reduced risk of thermal damage in case of electrochemical grinding as compared to the conventional grinding, because workpiece is all the time in contact with the electrolyte, which has very low temperature, or it is around your room temperature or the place where you are performing this operation, because the work surface is all the time in contact with water having low temperature. Cost of ECG is comparatively low comparatively low as compared to cost of conventional grinding. ECG machine tool is more expensive, but due to much higher material removal rate, per unit volume removal is cheaper, because material removal rate, as I have mentioned, around 10 times of conventional grinding. So per volume, per cubic millimeter removal by ECG is much cheaper than per cubic millimeter removal of material by conventional grinding. Machining area is made of non-corrosive and electrically non-conductive. Power supply to the grinding wheel is given by brushes. Mercury coupling can carry more current. Low probability of sparking. Abrasive grain always maintain a minimum gap between workpiece and wheel bonding material. Operations. Various kinds of operations of electrochemical grinding can be performed, like cylindrical grinding, form grinding, surface grinding, face grinding, and internal grinding. Now what I am showing this, that you can keep the workpiece and the grinding wheel in different positions to perform different kinds of operations on the workpiece. You can see here, this is the grinding wheel, this is the workpiece flat surface. This is known as surface grinding. Slowest because of small area contact between workpiece and grinding wheel. You can see here the area of contact is very small, hence it is slowest grinding process. Face grinding, fastest because of largest area contact between the workpiece and the grinding wheel. This is the face grinding. This is again the surface grinding. Sorry, this is not for face grinding. You can ignore this particular figure. I will show you later on what is the face grinding. Bonding material used is copper, brass, nickel. Reverse the current and the process will do ECG will do ECG on scrap workpiece. Deplate the metal bond, exposing the, this is for declogging and dressing the grinding wheel. You can reverse as written over here, reverse the current so that material is removed from the grinding wheel and worn out abrasive particles are removed from the grinding wheel. Forget about this particular figure, please. Sorry for that. Dressing is there. Now you can understand this dressing and other things. Here you can see clearly, for this purpose it is fine. It is not for this purpose. This here for dressing of the grinding wheel, you can see grinding wheel has been made as plus and workpiece has been made as minus. That is, this is cathode, this is anode. So material is being removed from the anode over here so that you can do the dressing of the grinding wheel. So this is for dressing of the grinding wheel. As you can see here, this is the grinding wheel and this is the workpiece. So for that purpose this figure is alright, but face grinding figure I will show you later on. Applications: economical in grinding carbide cutting tools, because carbide cutting tools are very hard, but with the help of electrochemical grinding you can do it easily. Electrochemical ground cemented carbide workpiece, no damage to microstructure and micro cracks. For reprofiling born locomotive traction motor gears, you can use electrochemical grinding. No effect on gear hardness. It is not going to affect the properties of the component in case of ECG, because in grinding, conventional grinding, because of large amount of heat generation, the thermal damage takes place, mechanical properties may change, but in ECG it is not so. Burr-free sharpening of hypodermic needles, this is another very important application. Hypodermic needles you can grind and remove the burrs, all the burrs. Superalloy turbine blades and honeycomb metals, there also you can use the electrochemical grinding process. Now you can see some of the devices which have been machined or finished by photochemical machining, we will see, but they can also be done with the help of electrochemical grinding. So one part can be made by different processes, that's why I have shown it here also, and I will show you this in photochemical machining also. By ECG you can see over here, you can see here, this is the part which is having the burrs over here and rough surfaces are there, and this is the part finished by electrochemical grinding. Now compared to this, there are no burrs and surface of the teeth is much better. So two identical gas turbine component made from a tough superalloy. The part on the left had the slots produced by ECG and the part on the right was produced by conventional milling. So you can see here the rough surfaces and burrs, there are no rough surfaces and burrs over here. Conclusions: in this lecture we have studied the following: working principle of ECG having three zones. Zone 1, it is pure ECM, electrochemical machining is taking place. In zone 2, both abrasion by the abrasive particles as well as dissolution, electrochemical dissolution by ECM principle is taking place, and in zone 3 only electrochemical dissolution is taking place. We have seen the essential components of electrochemical grinding machine tool. We have also seen the basic electrochemical reactions taking place in the inter-electrode gap between the grinding wheel and workpiece, and I have already told you the ferrous hydroxide and ferric hydroxide are being formed and there is no consumption of the electrolyte, hence the electrolyte is recirculated. We have studied basic parameters analysis of the process, and finally we have also studied some applications of the ECG processes. Thank you very much.